Hello everyone, welcome to topic 5.10, multi-step reaction energy profile. By the end of this, you should be able to represent the activation energy and overall energy change in a multi-step reaction within an energy profile. So prior to this, we looked at reaction mechanisms and how we have slow steps and fast steps, or slow elementary reactions and fast ones. We're now going to apply this to a topic we covered earlier where we had our energy profile or energy graphs and combine the two concepts. So reaction energy profiles can also be used to illustrate a multi-step reaction as long as the energetics for each step are known. In a two-step reaction, two transition states are shown, so that's two hills. And in a three-step mechanism, there are three transition states. The rate-determining step is illustrated by the energy of the transition states, where the highest activation energy corresponds to the slowest step. Intermediates are shown as valleys here, or troughs, if we're talking like some math or wave terms, between the reactants and the products. The placement of the intermediates is dependent upon the energetics of each step. In the potential energy graph on the right, the overall reaction is exothermic because the products are lower in potential energy than the reactants. However, the first step is endothermic because we see that the intermediate here is higher in energy than the reactant, so you must put energy is absorbed by the system first before it is released. This is also the rate determining step because the activation energy for this first step is much higher than the activation energy for the second step. And so this would also be our rate determining step. A reaction profile diagram can also be constructed from this type of information. So in the two-step mechanism below, T-butyl bromide is transformed to T-butanol in the presence of hydroxide. So when we look at this, we see that this overall reaction is exothermic, right, based off the differences here. We'll look at those later. So we add them together, we see there's a negative 10 kilojoule per mole change. So that means that the products are just a little bit lower in energy than the reactants. The first step, however, is rate limiting and is endothermic, right? So the intermediate is much higher in energy than the reactants, okay? And so that also proves that the first step here is a slow step because it has a much higher energy requirement. So it is going to be a rate determining step, that first step. Okay, so we are going to sketch a reaction diagram for a three-step mechanism that is overall exothermic. So it didn't give us a whole bunch, but we always start with our graph where this is potential energy. And this on our x-axis is our reaction progress. Okay, and it says that this is overall exothermic, which means that my products must be lower in energy than my reactants, lower in potential energy. And then it has three steps, which tells us it's going to have three hills. It doesn't tell us any other information, so we can leave it up to our imagination. And I have to redraw that one. So this is my reactants, this is my products. I have a three-step, and my overall reaction is exothermic. So this can vary. The big thing that it must have are the three hills, or three activated complexes, and that the products must be lower than the reactants. Okay, let's look at the WeDo that actually gives us real data. So we are going to draw the reaction energy profile of the diagram with the following data. Okay, so my products are at 5, which would be here. So this is my product. My reactants are at 20, which is here. Okay, so there's my reactants. And then my transition state 1 is at 80. So somewhere I'm going to put a little dot saying here's transition state 1. And then I have an intermediate at 50, so I need to find where 50 is, so about here. And I just need to have them in order so that my reaction shows it's making progress. And then transition state 2 is at 90. So I'm going to put it, I guess, here. This looks like this is 90, and I'm making progress. And now I connect the dots. Making sure I show 2 hills for a 2-step reaction. And this is all you would do. Okay, so using these concepts, complete the you-dos. Please check your work, and thank you so much for tuning in.